Morning, y'all. I'm working on that. I'm almost done with that question distribution for the old exams. Sorry I didn't get it up on Friday. I was out of town. But I'll have it up this morning before lunch. Okay? It'll be on the old exam side. I won't come out of notes, just to look and see it. All right. What? The question distribution, like where I say which questions for each exam, like we had last year. So if you want to practice from the old exams, which I recommend, you can do so.
You can also link the site to the Moodle page.
The what?
You also link the site to the Moodle page.
Is it not?
It's not. First thing with the thing we had to get to your old email and
Yeah, it's not on the Google site.
I'm sorry, I meant to do that. All right.
it kind of reminds me of things the Katie does. They'll write across the top and write in blood pressure, heart rate, O2 stats, and other little information down here, and they'll have it on their glove where they'll write it on a piece of paper later.
Yeah, this isn't quite as quick. Otherwise, going to die.
Yeah, no.
I will get it up
Don't
there.
worry, I'm in ER.
It's more convenient for you.
Can't do jack, bud.
So this test on Friday, which y'all can come to, 15 minutes early. I'll have it available to you at 7:15. You can come in at 7:15. Is that clear? Yeah. 7:15 on Friday. You can come at 7:15. You don't have to, but you can. Is that clear? All right. It'll be all of Chapter 1 and then a portion of Chapter 2, probably up to capacitors. We'll see sort of where we get to in the next couple of days. Have any questions? Feel okay with Chapter 1? Chapter 1 was largely Coulomb's law and fields. That was it. You'll have a 2D vector problem on the test. It could either be fields or Coulomb's law. Just make sure you can do that. You will see it. There are some old examples in the previous exams that you can see to practice, or in the homework, of course, or something. You had a good weekend?
It's interesting.
You were working, right?
Mm-hmm. Nothing too big or exciting.
Okay. All right, let's get started on electrical energy. We're going to be dealing with potential, but potential is really just a measure of energy. So you remember how we had fields? Do you remember how we defined what fields were? They were what per what? Something per unit charge. They were a way of describing the electric what? Force, right. So fields are just a way to measure or to describe the electrical force. And in a similar way, potential is going to be a way to describe the electrical energy. So where fields were force per unit charge, fields are going to be, at their most basic level, energy per charge. So the potential, which you know more readily as the voltage, right, the 9-volt battery, that provides 9 volts of energy per unit charge, or joules per coulomb. So whenever you think of potential, you want to think not of forces or fields, but you want to think of energy. How much energy is given to a charge? And this idea becomes important when we get into circuits. I'm not going to spend a whole lot of time on this, and it might not help you a whole lot. There are some basic ideas that I want you to know that I'll try to highlight as we go along. But it might help you to sort of understand potential and how we relate potential and energy. But first of all, electric forces we know to be conservative. Do you recall what conservative means?
To conserve energy.
Right. So in the physical world, in physics, whenever we say that something is conservative, we mean that it conserves energy. So this conserves energy. We had said that gravitational forces are also conservative. Does anybody remember a good example of a non-conservative force? That is a force that does not conserve energy. Okay, any force basically that requires contact between two surfaces, but in particular we said what was a really great non-conservative force?
Fluid motion?
Huh?
Fluid motion? Or?
No. This force always takes away a lot of energy. Friction, right. So a frictional force is a good non-conservative force because whenever it acts, it takes away energy. I also say that conservative forces are path independent. That is, if I take an object and I move it from here to here, I've done work on that object, and I've increased its energy, right? I've given it a certain amount of potential energy, that gravitational potential energy. But likewise, if I take this object and I have it here, and I move it through a larger path, and I move it to here, I've increased the energy by a greater amount or the same amount? The same, right? Because remember, gravitational potential energy was just mgh. It was just dependent upon the change in the height. It doesn't matter the path that you take. So for conservative forces, they're path independent. Now let's see. A force that conserves energy is a conservative force. So that means that the amount of work done by the force changes the energy by the same amount. Hey, Eric. Morning. All right, so what we're saying here roughly, if you just want to write this in an equation form, or you can write out all those words, or you can just say that the work is equal to my change in energy. And that was true for the gravitational force. That's true for all conservative forces. What are types of conservative forces? If a non-conservative force is a contact force, what is a conservative force in a general sense? Gravitational force is an example of one, right? Field forces. So these are examples of field forces, or field forces rather, are conservative. So that means gravitational, but also another field force that we know of is the, okay, yeah, magnetic, but the electric force, right? The electric force doesn't require contact. And then non-conservative forces don't conserve energy. So this is not true for non-conservative forces. And friction is a good example, because it doesn't matter the path that you take for a frictional force. The longer the path, the greater amount of energy that you're going to lose. Right. Now the work done by conservative forces is path independent. This stuff is going to sort of lay the groundwork for what we're going to do later, but it's not terribly consequential. It is important, but sort of in the mechanics of what we'll do, it's not terribly consequential. But you might see some multiple choice questions regarding some of this information about forces being conservative or non-conservative, path independent, path dependent, all that jazz. And then the work done by non-conservative forces is path dependent.
I wonder what all that jazz came saying from.
I don't know. I had a friend in Austin that used to say it a lot. Hung around him a lot, so it's kind of goofy, isn't it? I think it was like from the like in a song. Huh? Probably so. All right. I'm gonna skip this slide, business. But you might remember this. It's just saying that if I change energy from here to here, that this guy faces a certain amount of energy that he changes. But this guy, because of the frictional forces that are acting, he's going to have a lesser change in energy because that friction will actually take away energy. You remember this from last semester? No? Let's not worry about it right now. It's not terribly important. Okay. Now, we can make this argument about energy and work. Let's imagine that I have an object and I start it here, so this is my initial position. And then I move it up through a distant x, so this is my final position, xf. Now, the work that is being done by the gravity, is it going to be a positive or a negative work? The work done by gravity. Remember how we found out if work was positive or negative? We asked ourselves, what is the direction of the force and what is the direction of the displacement? ticking. Okay, remember if your force and your displacement were in the same direction, that was positive or negative work? That was positive work, right? It increases the amount of energy. And if your force and displacement are in opposite directions, that is negative work, because it's actually decreasing the energy, right? It's slowing the object down if you're moving in one direction, but your force is in the opposite direction. All right, so here I have a force that's down and a displacement that's up, and so that gives me positive or negative work.
Negative.
Right, so this gives me negative work. When I move from point A to B, I get a negative work, right? So that's where that negative comes from. But because this is a conservative force, I can say that the change in potential energy is equal to the work. That's because this is a conservative force. Right? Now, so delta PE equals negative work from A to B. That is equal to the negative of the force times delta X. This is going to be the force due to gravity, or the force weight. And so I get this expression, delta PE is equal to negative mg delta X. Or more generally, that delta PE, the change in the energy, the change in the potential energy in this case, is equal to the negative of the work. All right? So this negative comes about from this argument about the changing energy in this gravitational field in this case.
The AB would be
From point A?
point A to point B.
Right, moving from point A to point B. Because it's going to be the opposite if you're moving from point B to point A. All right? So, in a similar way, and this is sort of what we're building up to, is that the potential energy, the electric potential energy, is equal to the negative of the work, right? And that negative of the work is going to be negative of the force through delta X, just like we had with the gravitational force. But here the force is something different. If we're moving in a gravitational field, that work is equal to m times g, or rather, excuse me, the force is equal to m times g. But when we're moving in an electric field, the force is measured by q times e. That's based on our definition of the electric field. So this is equal to negative QE delta X. So we have delta PE is equal to negative QE. That's the force times delta X. That's just a restating of the work. Goodness. All right. Let's not worry about this aside. It's not terribly important right now. All right, you with me so far? You'll see why this becomes relevant in just a second. This applies when the electric field is constant. So that's sort of an underlying idea that we'll have, is that the electric field is always constant. And that's not a terrible assumption, that the electric field usually is constant when we're dealing like a laboratory setting where we can describe the electric field or define the electric field ourselves. All right, so let's look, for example, I have this these two metal plates, and I have a positive plate and a negative plate. And the electric field causes the charge to move from point A to point B. Has the electric field done positive or negative work? Let's use your clickers. We'll bring them out soon anyway, but go ahead and get your clickers out. A is positive, B is negative, and then just keep them out. We'll use them in a bit. So has this electric field, has it done positive or negative work on this positive charge? Positive or negative? Yeah.
Which is not
Okay.
so they like credit.
No, I'm sorry. Just hang on. You know, if you miss a few questions, it's not a big deal. In fact, I don't think we're going to do a whole lot of questions today. All right. Just a few more seconds. 48. so A is right. It's done positive work because the force and the displacement are in the same direction. So we've done positive work. And has the potential energy of the charge increased or decreased? The potential energy. Has the potential energy increased or decreased? A increased, B decreased. All right, I'll stop at 38. Okay, it is B. And this sort of comes about from this argument where we have that the change in potential energy is equal to the negative of the work. And since the work is positive, that means that delta PE is negative. So we have a negative delta PE because our work is positive. Now, if our work was negative, it would be a positive change in potential. And you can think about it too that, I have this force pushing on this particle because notice it sits in this electric field. And remember, the electric field, the direction of the electric field is the same direction as the force on what type of particle? A positive or a negative particle? The direction of the electric field is the same direction as the force on what? A positive or a negative particle? Positive particle, right. So that's how we determine the direction of the electric field, right? We take our positive test charge out of our pocket and put it in the field and ask ourselves what's the direction of the force. Because the force and the field, they're the same basically. The field just describes the force. That sounds very ominous, doesn't it? The field describes the force. Okay, so this might seem ridiculous to you, but it's useful. Well, it's not terribly useful actually, but it will become useful when people begin to use electricity. Okay, so if positive work has been done on the charge and the potential energy is decreased, what happened to the energy of that charge? Like we know it's a conservative force, so we know it wasn't lost to heat or whatever. We know the potential energy decreased, but work was being done. So what happened to the what is the energy? How would you describe it? It's kinetic energy. So right, that energy has become kinetic energy. Or the work has created kinetic energy. You ever read Fancy Nancy? No. You ever read Fancy Nancy? You read Fancy Nancy?
What's Fancy Nancy?
It's a book. Yeah. It's like a little girl book, Fancy Nancy. But anyway, this is a fancy way of saying that the charge is sped up, that the charge is increased in velocity. So you use this electric field to increase the velocity of the charge. Which I already knew that, right? So that's sort of the punchline here. So the charge has lost potential energy at point B. Its kinetic energy must have increased. Then we can also calculate the charge's velocity at point B. So we can say that delta KE is equal to the negative in the change of potential energy, which is equal to 1/2 mv squared. Or you can think of it in this way, that the work done on this particle equals our change in kinetic energy. That is to say QEX, which is our work. That's our force times our displacement. Our force is QE, where F equals QE. Work equals F times X. So this is our work, QEX. And our kinetic energy is 1/2 mv squared. It's a pretty useful relationship, that if I have an electric field and a charge moves a measured distance through that electric field, I can either, if I know its mass, I can determine its velocity, or if I find its velocity, I can determine its mass, and that might even be more useful. If you measure the particle's velocity, you can find the particle's mass. All right. Let's just try the simple problem, and then have a proton release at -2, an electric field of 1,000 newtons per coulomb. What is its velocity at x equals 8? Why don't y'all try that? Just take a couple minutes to get started. Remember to convert your distance to meters, and be careful on what your delta x is, because it's going from -2 to 8. So what is its total distance? Alright, so we say QEX equals 1/2 mv squared. Y'all can keep going, I'm just going to catch you up here. What is my distance it travels?
2 centimeters, 0.1 meter.
Right, in the SI system is 0.1 meters divided by my mass. I get 140,000 meters per second, keeping 2 sig figs. I should just keep 1, but I'll just keep 2. Alright? It's pretty fast, huh? So what y'all got? That's a simple problem, but that's a very useful relationship that allows you to determine a lot about unknown particles. All you have to know is their charge, their mass, or their velocity. You can find any one of those things. All right. We'll talk about this later when we get into magnetic fields, because this concept was used to determine like the mass to charge ratio of the electron, for example, and is used in a lot of instruments as well to find the masses of unknown particles. I go down from here. Is that exciting to you? Like that's a big chemistry thing, right? That you use stuff like this to find unknown substances. Oh, and the crackers, wow. Oh, okay. All right. Yeah.
Change in X.
Yeah. Right. Yeah, x final, that's delta x always. And so that's 8 minus -2, which is equal to 10. Because I'm going from -2, going past the origin, up to 8. So this distance is 10 centimeters. Tired. Right. All right. All right. So let's look at, we're going to look at potential and potential difference. We which are going to be related to this. Now, potential, we said at its sort of basic level, is a measure of what for what to what per what. Like if fields are a measure of force per charge, potential is energy per charge. Potential is a measure of energy. And when we talk about potential versus potential difference, potential is energy per charge. Potential difference is just the difference in potential between two different points. And whenever we talk about potential difference in electrical circuits, we're talking about that, the difference between two different points. All right, so the electric potential difference between 2 points A and B is the energy per charge gained. As the charge moves from point A to B. Because remember, V, at its basic level, this is potential. Is equal to energy per charge. And we need to figure out some way to give these charges energy so that they can travel through a wire and do whatever it is that we want them to do. Light a light bulb, run a motor, whatever it is that we want them to do. All right. So delta V is the difference between the potential at point B and the potential at point A. And that's equal to a change in potential energy over Q. The units of voltage are a joule per coulomb because it's energy per charge. And so this is going to equal 1 volt, which is the name of a person. Do you know the person it's named after?
Something volt?
Volts. Volts. It's the shortened part of his name. Voltaire, right. So it's named after Voltaire. And since it's a person, we abbreviate, or we capitalize the abbreviation. All right.
For some reason, I want to see something named Hutchinson because that just does not sound like the name of anything that could
No.
be E.
I think if it was a scientist named Hutchinson, they'd probably just name it a Hutch. But that's not a very good sounding unit, is it? But we'd probably get used to it. 1 Hutch. All right, so delta PE.
But that just be get confusing in a place where there's Hutches.
Right. So delta PE, remember that was the negative of the work, so that's negative QE times delta X. This is just saying that delta PE, we've already said, is the negative of the work. And so delta V then, if it's going to be defined as delta PE over Q, then that's going to be negative QE delta X over Q, which is going to be, see, this is a delta X. The Q's will cancel out, and it'll just be negative E delta X. Getting to something, we want to describe the electric field in terms of the voltage. So, we can describe the electric field here in terms of the voltage like this. It's going to be negative delta V over delta X. Later, we'll come back to this. That's why I'm sort of going through this. Right now, it's not terribly important. Though I want to show you 2 things. First of all, normally for electric field, we give the units to be 1 Newton per coulomb, but we'll also give the electric field in 1 volt per meter. And that's more common to give the electric field in terms of volts per meter. And it's because of this relationship that the electric field in terms of this work is the same as our potential over our delta X. All right, y'all hang on. I know this is kind of dry, and it is kind of dry, and not all of it we'll come back to. I'll go back and I'll show you sort of the things that you'll need to focus on. But this relationship will come up later as well when we describe the potential in terms of the electric field. Because later, I don't know if it's going to be on this next exam, but later we'll see that the electric field is equal to the, what does delta usually mean in calculus? Right, but what is it usually leading to? when you do a derivative, right? And so we'll describe the electric field of the derivative of the potential in terms of position, which is, will come up later. I'm going to put in a little cloud right here. That E is equal to the negative of the derivative of delta V with respect to x. But this is called a partial derivative, so it's a little bit different than what we've done before. All right? Is that exciting? Have you ever done partial derivatives? They're just like derivatives, so they're a little bit different. Yeah, they're simpler, right? I like them. All right? So we'll get into that later. Probably not this next test. We'll see. All right. Jose?
Is there any special meaning for the 3 lines that you put in the equal?
Oh, this is a definition. So this isn't equals. I mean, it does mean that it's equals, but it means that delta phi is defined as.
Just curious.
I use it occasionally. It's just saying this is blah. Like we're taking the potential and we're just going to make it up and we're going to define it as the energy per charge. We had a similar thing for electric field. We defined the electric field as the force per charge. The force per charge are two physical quantities, and then we're going to take them, put them together, and we're going to define that as the electric field. It's not a physical thing per se, but it's based on physical things. Something we made up. We make up a lot of things, like in science. We make up a lot of things to describe other things.
I knew it was all made up.
Right.
All
Yeah.
our heads.
Huh?
That are also made.
Yeah, y'all appreciate this when you go into PChem. I think it's the first semester. That my quantum mechanics professor, is that quantum PChem 1? That quantum mechanics is basically just all made up to describe the data. Because you don't really know why it is that particles act in the way that they do. But it's all just sort of
We're all guessing.
a framework to
We're still
describe
guessing.
what's observed. Yeah.
Quick, what is the Higgs boson? No.
Right. Okay, so let's skip this first sentence. Sorry, it's not. Carry this down for y'all as much as I can. So, all right, so we have a couple of rules, and these will come up, that positive charges accelerate from high to low potential. The way I always remember this is I think of this setup where I have these two parallel plates, which are two charged plates. We'll see if this is a capacitor, basically. But you have two charged plates with positive charges and negative charges. So I have my positive charges over here and my negative charges over here. Now, the positive side is the high potential side. And the negative side is the low potential side. So if I imagine a positive particle here, it's going to feel a force in this direction, and it's going to cause it to move from left to right. And that's going to move from high potential to low potential. All right, from high to low. Because over here, I have a positive V, and over here I have a negative V. I'm moving from high to low potential. So negative charges, if I put a negative charge in here, which way is it going to move? To the right or left? Which way, Chris? It's going to move from low to high. It's going to move to the left. Right. So negative charges accelerate from low to high potential. Positive charges accelerate from high to low potential. Negative charges accelerate from low to high potential. And if you forget those rules, it could come up in your multiple choice. I'll show you a similar problem over here in just a second. Just remember this this setup where I have these two charged plates. Positive are going to move from the positive to the negative plates. That is from high to low. And negative charges move from low to high potential. And that's completely irrelevant, right? Yeah, it's not though, because you can set up potentials in the lab, and then you can basically cause charges to move around by the potential that you set up. Let me show you. So say, for example, I set up this potential in the lab, and I have a particle, and I release it, I have a positive particle, and I put it at x equal a. So this is x equal a. And I want to know, oh man, the right answer is, I'm sorry, the answer is it's going to move to the left, right? That a negative particle, if I release it at point A, negative particles move from high to low. Right. Or excuse me, positive particles move from high to low. If I remember my plates like this I have set up, I have a positive, negative plate. This is high, this is low. My positive particle will move in that direction. Right. So if I release a particle here, it's going to move in this direction. What's going to happen when that negative particle, or excuse me, when that positive particle, when it gets to the bottom? What is it going to do there?
Jump around, I don't know.
It's going to jump around, right? Because it's going to
have enough velocity to go over the next one.
It might have enough energy to go over. So
Head down to the lowest.
imagine, you can sort of think of it as like a ping pong ball in a bowl, right? It's going to come down here along this potential, going from high to low potential, and then here, and it might come up a little ways, and it might keep going over if it has enough energy, but if it doesn't, it's just going to oscillate back and forth, back and forth, back and forth. This is called a potential well.
You'll never reach rest.
Huh?
You'll never reach rest.
No. Well, I don't know. I mean, it must lose energy somehow. I'm not sure. I don't think so. I guess when you remove the potential, right? I mean, because you're putting energy into it by creating this potential. Yeah, so that's where the energy is coming from the actual potential that you're setting up. So no, as long as the potential is there, it will stay there forever. All right. What happens if I put a negative particle right here? Right, it's going to move to the right. Right? And in fact, when it comes up this potential and it moves to this position, what's it going to do? It's going to do exactly the same thing. So see this well, it looks like a well over here, but you can have the same thing over here. It's going to move back and forth, back and forth, back and forth. So a positive particle would move to the left. A negative particle, there are two correct answers here. It would move to the right, but it would also oscillate around B. All right. So why is, because once it goes over this hump, a negative particle wants to move from low to high potential, but you see if it's here, it wants to go back in this direction. So it's going to shoot back over, and then it's going to get here, and it's going to say, oh crap, let's move back over in this direction. And then it's going to get here, and it's like, oh no, and it's going to go back and forth, because it wants to move from low to high. But it overshoots just because it has energy, and it's going to go, it's like that ping pong ball in a bowl. You shake it back and forth, and you can oscillate them there at very regular frequencies. All right. Those are often used for like timers. I know at least in like radio astronomy, you need very accurate timers, and you can put charged particles in a potential well, and they become very accurate timers because they oscillate at a very regular frequency. Kind of like the cesium atom. Remember the cesium atom was a standard for the second at a very regular frequency. You can do the similar thing just with charges. Well, that is a charge. All right. I know this is really dry, and the circuits will be a lot more fun. This can be difficult, and it doesn't really seem like it's very relevant, but it is sort of relevant for the underpinnings of when we get to circuits. Though when we get to circuits, like we're going to sort of forget about all this anyway.
All my motors still work.
Right.
I have like a series of like almost 100 different things, different little fans. Like I've broken a number of my little electronic toys and stuff.
I guarantee you that if you don't understand this, that your motors will not work appropriately. Right? So why is this important? Because you can, by creating these different potentials, which is what we do in circuits, basically. You know, we create potentials with batteries and resistors and all sorts of jazz. you can move charges around at will. And that might not sound like something you want to do on the weekend, but it's actually very useful to be able to control these charges and where they go, because they carry energy and you can use that energy in other places. So by creating these potentials, you can move charges wherever you want.
So it's just like a charge of battery, things like that.
Hmm?
Don't need to sense charge of batteries, battery, car battery, charge it.
You're actually.
Energy from that charger, putting it into a lower version of that battery, I guess.
Mm-hmm. We'll talk about that. I mean, you're converting their electrical energy to chemical energy. When I talk about this, like in a circuit, for example, with a battery, if we think of a circuit, say I have a battery here. This is a battery symbol. And I'm moving charges through this wire. This is going to be my high potential, and this will be my low potential. If I call this point A and this point B, the potential V versus X, this is point A, this is point B, the potential will look like this. Because I'm moving a charge from a high potential to a low potential. Now that assumes what type of particle? What type of particle moves from high to low? Positive, yeah. So we know that in circuits actually it's not positive particles that move through the wire, but when we talk about circuits, we think of them as positive particles. All right? That's because of Ben Franklin rules. We'll talk about that later. I forget what your question was, but did it answer?
Yeah.
Okay. Oh yeah, with the charging batteries, yeah. So you're taking electrical energy and converting it into chemical. We'll see that later.
What is that arrow going to?
What arrow? Right here? Right here? Yeah, that's just saying that I have positive charges moving in this direction. Moving through that circuit, that wire. But if I were to look at this, if I were to plot the potential, it would be like having those charges move from here to here. That's a plot of the potential versus position, which is similar to the plot that we had right here, except that was a more complicated potential with wells and what have you. All right. Let's see. What's next here? So if you're in the lab, you played with these. You can go and look at these on your own if you like. They're kind of fun. You can play around with charges and fields, and you can draw equal potential lines and what have you, which we'll do later. Let's try some of these questions. These are in the back of your book if you want to follow along there. Stop at 105. Very good. He's the right answer. This sort of goes back to chapter 1, right? That we actually, yeah, if we think of the field, that there's a field in here, and the force due to the field is equal to Q times E. And since they both have the same charge, they both feel the same force, because they're in the same field. But since they're oppositely signed charges, they're in the opposite directions. has the larger acceleration? The electron or the proton? Or both, or neither? Stop at 35. 35. B is right. Why does the electron have a larger acceleration? It's what?
Smaller TT per scram.
Right. It has a smaller mass. So F equals ma. What was the answer? It was B. So small mass gives me a large acceleration, given the same force. After they move through this potential, which has the larger energy? Proton, electron, the same, or neither? I'll stop at 1 minute. Okay, is kinetic energy, is it a vector or a scalar quantity? It's a scalar quantity, yeah. So it doesn't have a direction assigned to it. In fact, you can't really have a negative kinetic energy. I know that work is also a scalar quantity, and we sometimes talk about it as negative, as meaning like taking away energy, but kinetic energy is never negative. So C is the right answer here. They both acquire the same kinetic energy. I can understand. Oh, no.
Even though they're different masses?
Yes. So remember our voltage is energy per charge, right? They both have the same potential difference that they're going through, and they both have the same charge. Now, one of them is going to be moving faster, right? And so you're thinking, well, it's going to be moving faster, so it has more kinetic energy. But that's also the least massive of the two. And so we'll see that the way that interplays is that they'll both have the same kinetic energy, the way those two variables interplay. All right? They're based on this definition of voltage, energy per charge. It's not dependent upon the mass. The energy is only dependent on the voltage and the charge. You with me on that? Yeah, I thought most of you got it right, but that's not the case. Most of you got it wrong. Okay? Voltage is energy per charge. Okay, we'll get to this later. We might get to it next time. We're going to continue on. I want to go ahead and define to you what potential is. So we can determine the electric potential due to a point charge. This is on your equation sheet. You'll need to know it. And we'll calculate the electric potential due to a number of point charges on the exam on Friday. The electric potential due to a point charge is KQ over R. And when R is equal to infinity then, if R goes to infinity, what is our voltage? If I'm an infinite distance away from a charge Q, right, if R goes to infinity, our potential goes to 0. All right.
This equation, should we write that as a limit?
Hmm?
Shouldn't we write that as a limit?
I did an error when R goes to infinity. That's like a limit, right? All right, so we have to derive this through calculus, and we'll look at that probably for the next test, but we can sort of do this ad hoc sort of dimensional analysis. Yeah, that delta V is equal
Is
to
that our next word for us to use today?
ad hoc.
Yeah.
Yeah, you should be using that word every day anyway. I assume that you are. Do you not?
What is ad hoc?
Ad hoc, meaning that it's sort of a, I don't know, a loose. It's not really a derivation. It's just sort of something you make up. It's not real rigorous. It's ad hoc.
An imaginary.
Andrew's going to look it up. Ad hoc and equidistant at the McDonald's counter. All right.
Can you actually figure out a
That
sentence
is
to
bad
use
as
both of
order.
them?
Huh?
Can you figure out a whole sentence to use both of them?
I'm sure we could figure out something. All right, so this is delta E times delta X, and I know that E is KQ over R squared. We can just replace our delta X, wave our hands, and say delta X is a distance, R is a distance. And so we get KQ over R, that our potential is KQ over R. And that's just sort of a dimensional analysis. It's a scalar quantity. It's unlike the electric field. So the potential of multiple charges adds algebraically. That is, say that you just add them up like numbers, not like vectors. It makes your life a whole lot easier. Or if you want to know the potential, you can find the electric field based on the potential, but it just adds up algebraically. All right. Let's try this question. This will probably be our last thing. Which of these statements is true at point P, which is the center of this square? Which of those? Is the electric field 0 or non-zero? And is the potential 0 or non-zero? Now let me just help you out here. So imagine that I have a, I'll go and start the counter, but imagine that I have two charges. Say I have a plus Q charge and a negative Q charge. I know that at a given point, say this point for example, that the potential due to this charge, let's call this R1, the potential at that charge, V1, I'll call this Q1, is equal to K times Q1, which is positive, over R1. And then the potential due to this other charge is going to be K times negative, I'll call it Q2, let's be Q2, divided by this distance, which is R2. And then the total potential at this point is going to be V1 plus V2. Is that potential going to be positive or negative? It's going to be negative. Or no. Yes, negative.
Oh, we're going by the way you drew it, or?
The way I drew it, yes. So I'm a further distance away. No, it's going to be smaller. The negative charge contributes less potential than the positive charge. Right. So since R2 is bigger, that means that V2 is less than V1, and so this is going to equal a positive number. You follow what I mean by that? What if I were equidistant between the two charges? What would my potential be? It would be 0, right? Because V2 and would equal V1, the two distances would be the same, but one is positive, one is negative, so it goes away. So try this question. Here, instead of two charges, you have four charges. I want to know what is the potential due to those four charges, two positive, two negative charges. And I also want to know what is the electric field. Now you'll need to draw the electric field vectors at point P due to each individual charge. So I knew due to this charge, for example, the electric field vector is in that direction. What do the rest of those electric field vectors look like? We're almost out of time, so. I'm just going to tell you the answer is A, so y'all go and click in, the time's up. You're going to click in A. and I will show you. Just give me kind of 10 more seconds, please. 10 more seconds. 240, I'm stopping. Click NA. All right, so look. The electric field due to this charge is in this direction, due to this charge is in this direction, and due to this charge is in that direction. So the electric field is 0. And because I have equal numbers of positive and negative charges, and I'm equidistant from all of them, my potential adds up to equal 0. We'll go over that next time, and that'll be on the test. Now, I don't want to put a whole lot of stuff on this test. I'm not terribly concerned about getting too far into this chapter, because we have 4 more tests after this. Exams. It's called exams.
Is there going to be a new material next class?
Yeah, but we'll have some review time, maybe a half hour or so. So if you have questions, please bring them next time.
At least we have upgraded from tests.
Right. They're full-fledged exams.